Thanks. I didn't start my career in teaching. I went out and did some work in applied mathematics, but came around to the idea that teaching was going to be more fun and interesting than what I was doing. Always wanted to do some teaching and helped build the online school at Art of Problem Solving. Wrote most of the classes there, taught them for a few years before leaving to start more of a local program, because part of what I believe is that what we need is not just more classes and more good material. We have some of that, more and more of it with the internet, but we also need some sort of a cultural representation of a community able to get together to learn mathematics. So I'm really glad to be here where there is such a community. Today's topic, we're going to talk about recursion. And before I talk about recursion, I'm going to do the boring thing first, which I usually don't like to do. But I think in this case, it'll help more people understand more. And I don't know exactly what level everyone's at. Some of this will probably be at your level. Some of it may be too easy. Some of it may be too advanced. But one thing that I want to point out, having gone to the Math Olympiad program in the first year, not being prepared for what I saw, I've got a little bit more respect for seeing notation explained. And the one notation I'm going to explain at the very beginning is this little thing right here, this number to the bottom right of F. And the capital F is usually what we use to explain the Fibonacci sequence. And we could, of course, use variables to explain a sequence, just A, B, C, D, but eventually we'd run out of letters, and we'd also have no system for enumeration, nothing to tell us where one is in terms of the other, especially when we go into a second alphabet and a third alphabet, which we'd need for more than 26 terms. So we use these subscripted variables. And we see the Fibonacci sequence explained very often with the first two terms, which are the same and both equal to 1. And then we have a recurrence relation. Some term is equal to the sum of the previous terms. It can be written in a number of different ways, but this n, just think of it as any integer. At the beginning, we usually think of it as any positive integer when we first start working with the Fibonacci sequence, but the truth is it can be any integer. We can even go into the negative integers, but maybe we'll see a little bit of that later. So if we make n equal to 5, then this relation means that f of 7 equals f6 plus f5. And the fifth Fibonacci number is 5, the sixth one is 8, and the seventh one is 13. And they always occur this way. It's the rule. It's how it is we describe them. So now, moving on to the more interesting part, I want to start with a story. And I call this exploring recursion, and what I'd like for everybody to get out of this is not just this topic, recursion. It's how to play with mathematics. It's what you can do to go home. And one of these results is actually one that oddly I had never actually come up with a good way to explain until yesterday on the drive here, just playing around with stuff that I hadn't quite played around with before because there's just so much of it. But here's the first problem we're going to discuss. Say there are two students, and in the packet I used two of my old students, Pushkar and Jimmy, and they're at the beach and they're drawing stuff in the sand, and they start making sequences. And this is how the sequences go. There are stars. One of them draws stars and the other one draws squares. Maybe after the first list of symbols, they decide that there's going to be a rule. I've got one more than I need. They make a list of 12, and they decide that squares are always going to come in pairs. And that doesn't necessarily mean that there's exactly two at a time, but it means that each one has a neighbor with which it is married, and a star can't go between them. And so anytime we see squares, they have to occur an even number at a time in the sequence. And so this is the rule that governs this. And they start making different sequences. There are a whole lot they can make. And they do make a whole lot. And at some point, they ask a counting question. They ask how many such sequences are possible. And we'll add a little bit of mathematics to it. We'll come up with a definition. We'll use legal right here. Here's the rule. Squares must occur in pairs. And we call a sequence legal. We're going to count the legal sequences. If the number of squares in any consecutive sequence of squares is always odd, we can't have 1 or 3 or 5 in a row, not exactly. And so they keep making these. And they wonder, well, how many can we make? And there are different ways to approach this problem. There are a number of perfectly reasonable approaches and perfectly reasonable solutions. One solution that I've seen a lot of people move toward is to say, well, I can do this with casework. Casework is one of these early tools. It's a rather naive tool that we can use to approach a great many problems that we don't have a complete understanding of yet. And sometimes it's simply the best approach to a problem. Though with problems like this, we often suspect there may be something more interesting. But we'll see as we go. Well, casework. And what's a good thing to base casework on? We could base it on the number of stars or the number of squares, though really these are the same thing, because there's always 12 total. But I usually like to base casework on the thing that there are fewer possible numbers for. I mean, we could say there are 13 cases for stars, 0 stars, 1 star, 2 star. There are only 7 different cases for squares, 0 squares, 2 squares, 4 squares, so I'll do that. Fewer cases, so 0 squares. That would mean there are just 12 stars, and there's only just one possible sequence. It's pretty simple. Well, 2 squares. And we start thinking about 2 squares. Well, where could they be? Those 2 squares could be in, we could move the first one over. The first one could be in 11 positions. We'll sort of anchor ourselves to the first one for a good perspective, and we get 11 possible outcomes. Now, how about 4 squares? Well, 4 squares becomes a little bit tougher. We could do sub-case work. Hold 2 of them still, move the other ones around, move the first 2 over, move the other ones around. But this starts to get a little bit tedious. And, well, what if we looked at this pair right here as a married couple, and this one right here as well? And these have to move together. We can consider them like one unit. And now what we have are, instead of 12 symbols in a row, we can think of this as 10 objects in a row. And now that we have 10 objects, 8 of which are identical, the other 2 of which are identical, what we have is like a letter rearrangement, like 8 S's and 2 M's. We'll call this the married couple, and S for star. So, well, and it's a combination. For those of you who know combinations, it's going to look the same as a letter rearrangement. It is the same if we have 2 letters. Turns out there are 45 for this case. And already the casework looks like it's getting a little bit more complicated and a little bit more complicated. But this letter rearrangement or combinatorial method, combinations, this will do for the rest of the cases. But that's a bit of work right here, even just to get to this point. A lot of people are going to have to sit and think and play around before making each one of these observations. Coming up with a good model takes plenty of time, even if the calculation is simpler afterward. So we look for another approach. We look for something that might be more interesting. Another approach to this. Well, very often we find good approaches in mathematics. We solve problems by starting simple. I'm going to start simple. I'm going to count the number of legal sequences, not of length 12, but of length 1. And there's just that one, just a star, and then 2 symbols. Just those 2 possibilities. It's not so hard at first. There are 3 of them. A lot of people stop when they see a pattern and they try to fit it to the simplest possible pattern. 1, 2, 3, 4, 5, 6, 7, 8. One thing that we always have to do with sequences is to make sure that we understand the mechanism involved. There are other possible continuations of the sequence, 1, 2, 3. Well, let's see what we get for 4 symbols. I've seen some good problem solvers even trip up trying to count the ones with 4 symbols. It's very easy, especially as it gets larger. And really, this is the point right here, going from 4 to 5 to 6. For somebody who hasn't seen this problem before, if you don't already know the solution, it becomes tougher and tougher to decide when to stop. How do we know that we have them all? How do we know, even looking at a list and making sure that we don't have duplications or haven't made a mistake, including one that's illegal, it gets harder and harder. I'm going to go up to 5 symbols here. And I'm going to stop and take a look. I'm already getting lazy and some of my squares look like funny looking pieces of bread. When we get to this point, we've got 8. And a lot of people at this point become more confident that they recognize the sequence here. We are building the Fibonacci sequence. Well, maybe we're skipping the first one. Or you know what? Maybe we say, well, there's one way to make 0 symbols. There it is. And that's our 1. And then otherwise we start at 1, 2, 3, 5, 8. And, well, you know what? Just like I said before, anytime we find a sequence, there's more than one possible way to continue. So we want to be sure. We want to examine this and see, how do we know? How do we know that we're adding them together? And we're adding them together. What's some way to see why? And there are a lot of ways to go. When I'm looking at a sequence, I like to think about how it's built, how it's constructed from one term to the next. What are the changes that are going on? Why does it evolve the way that it does? And if I ask myself, how do I build legal lists of length 6? How can I do it? Well, at some point, any legal list of length 6 was, just before that point, a legal list of some smaller length. We built it up, and it was legal, and we kept adding more stuff to it. And just examining that, examining what the rule tells us, gives us a way to think, well, how do we continue to build? Well, there are 2 possible ways to build, just 2. We add a star, or we add 2 squares. So thinking about that, how do we build? We add 1 star, or we add 2 squares. Those are the only possibilities. And if I want to make all the legal lists of length 6, I can add a star to every legal list of length 5. Here's what's important about this. What's important is I know that I have built so long as all my work was correct up to this point, I have built every possible legal list of length 6 that ends in a star, because once upon a time, it had to have been a legal list of length 5. If I've counted all those correctly, then I've counted all the ones of length 6 that end in a star, and now I'm going to count the ones that end in 2 squares. And I can do that because I know that every legal list of length 6 that ends in 2 squares was once upon a time a legal list of length 4. And 2 squares were added on. And so long as my work was correct up to this point, I know I've got every legal list of length 6 that ends in a square. And those are the only 2 possible categories. So yes, there are going to be 5 plus 8, 13 of them. And now we've played around and we've discovered the mechanism behind this. And this is recursion right here. This is maybe the example of the simplest, I shouldn't say simplest. Fibonacci seems like the simplest recursion, well, that goes beyond looking at just one previous term. You guys have probably seen more recursive sequences than you think, at least those of you who are young. Here's one right here. 1, 4, 7, 10, 13, 16. What type of sequence is this? It's arithmetic, yeah. And if I wanted to, I could write each term as A1, A2, A3, and by definition, in an arithmetic sequence, we have a common difference. Here, that common difference is 3. And we could say, well, the sequence is defined by A1 is 1, and AN plus 1 is AN plus 3. And there it is, and that's a recursive sequence. Go one step further where we're including not just one previous term, but multiple previous terms, and Fibonacci may be the simplest example. So I think of this problem right here as the problem that opens the door to a whole lot of new mathematics. Yes?
Is there an easy way to show that if we add 2 stars to 4 symbols, we are getting something that's already covered?
If we're adding 2 stars to 4 symbols, then,
can you repeat his question?
Yes, the question is there an easy way to see that if we add 2 stars to a sequence of length 4, that we're not getting a new sequence that we haven't covered? And the answer is yes. This sequence right here is a sequence of length 5. And if our work was correct to this point in time, then we already have that list right there. There are only 2 categories. It ends in a star and it ends in a square. And ends in a square means it ends in 2 squares. And we've counted all those possibilities. If that's something that doesn't quite add up, it's something to think back over again and take a look at this problem again later. It's part of the reason I came with a handout so that you guys could take a look step by step through this. Are there any other questions about this? This would be a good time to ask. Now, I've given you guys, after the first 5 or so pages in your packet, if you take a look, there are about 5 extra problems. And one thing I'll tell you about these problems is that they're essentially all the same. And it's a good idea to work on these problems until you see the sameness behind them. But maybe I'll pick one to work, and then we'll go on to some things that are related. But step a little bit outside of Fibonacci. By the way, I'm going to tell you guys this right now. There is no way to proceed with this talk in the sense that I am here to explore. And whatever it is that you guys ask me, whichever problems in this packet you might be interested in working, we'll see where our explorations go. We'll just play up here on the board, and you guys can feel free to navigate the direction of this talk, at least to a large degree. So let's say that you're walking upstairs. And I remember being in middle school, just at the point where I got tall enough that I could take 2 stairs at a time. And that was such a wonderful thing because it saved time. With 5 minutes between classes, saving the 3 seconds maybe that it took to walk up 2 stairs at a time, it felt like I was saving so much, an eternity perhaps. Well, if we have a staircase, let's say our legs are long enough that we can take 1 step at a time, or we can stretch them on out and take 2 steps at a time. So there we are with 3 legs, which is what we need. And we take 1 step at a time or 2 steps at a time. We want to climb up, let's say, 10 stairs. And how many ways could we do this? Well, we could go up 1 step at a time, the classic way, the boring way. Or maybe we take the first 2 steps. There are a lot of places to take 2 steps. We could do that in the middle. We could do it at the end. A lot of places to move it around. And, well, what is this problem right here that we've already talked about?
Well, it's the exact same problem as last time, except instead of 2 boxes in a row, it's 2 steps in a row, and instead of a star, it's single steps.
Yeah, absolutely. This is the exact same problem. Recognizing when you've solved a problem before, being able to relate to that are perhaps couched differently, worded differently. This is one of the things that moves us forward in mathematics. Anytime we take 2 stairs at a time, we represent that with a pair of squares. Everything else, 1 step, we represent it with a star. And we're asking how many sequences, how many legal sequences of length 10 there are. And you know what? We never actually even answered the question previously with the stars and the squares. Got so excited about the recursion that we never answered the question. So let's do it right here. With 1 step, there's just one way to do it. With 2 steps, there are 2 ways to do it. "89 different ways we can walk up the staircase." Or if we went out to legal lists of length 12, as in the last problem, there are 233, which is not the friendliest of numbers. When you get to a number like 233 at the end of a math problem that's as simply stated as that one, usually feel like there's something going on other than the usual methods that you might use, permutations and combinations and nice blocks of counting that we might otherwise have. So, you know what? Let's make one more such problem. We'll add to my beautiful stick figure with a 4th leg. Now you've grown large enough that you can take 1, 2, or 3 steps at a time. Either that or the staircase is small enough. And how many different ways can we climb 10 stairs when we can do this? So this is a little bit tougher problem. And you know, just before we get too far into this problem, I'm going to go back and represent this with symbols. Perhaps 1 step is a star, and stars can occur 1 at a time or any number at a time. 2 steps at a time is 2 squares. And what can we call 3 steps at a time? Triangles. It's a good, easy symbol to draw. So this right here would be 1, 2, 3, 2, 1, 1. That's one way to climb 10 stairs. And can you help us get started simple? Help us get started simple, and then we'll come back for the general method.
This is similar to the Warlow series that you use in the packet, where it's like the Fibonacci series, except instead of adding the last 2 numbers, it adds the last 3 numbers.
We had the last 3 numbers. So let's see here. Let's start simple. I always do bad with names of past mathematicians, and half the time I'm working with sequences. I bet a lot of professional mathematicians will tell you half the time I'm doing something that I'm not familiar with on a day-to-day basis. I don't remember what it's called. I certainly don't. But let's see. 1 symbol. That's the only way to do it. 2 symbols. Got 2 ways to do it. 3 symbols. Let's see. Did I leave any out? Are we good here? So, you know what? Now that we've explored one of these problems, it's usually quicker to continue with the same kind of exploration. Let's do that. Let's jump straight to how it is we can construct the next level of sequences. Sequences of length 4. Well, 3 different categories. First category ends in a star. Second ends in 2 squares. And the third, it ends in 3 triangles. So let's see how many we can make. And in any sequence of length 4 that ends in a star must have still been legal when we'd written 3 symbols out. Had to have been legal at that point if it's legal after the 4 symbols. So what I'm going to do is I'm going to come over here and I'm just going to add 1 star to each of these. If there were any other possible sequences of length 4 that ended in a star, then there must have been some other sequence of length 3 that we could add a star to. So we've got them all. And now, if there's any sequence of length 4 that ends in 2 squares, prior to those 2 squares, we had a legal list of length 2. So if we have correctly listed them all, we can just add 2 squares. And any legal list of length 4 that ends in 3 triangles was once upon a time a legal list of length 1. So we add 3 triangles to each legal list of length 1, and there we have them, all the legal lists of length 4, 1 plus 2 plus 4, 7 of them. 7 different possibilities. And yeah, we do see we just add the 3 previous terms. So maybe we've got the Cordero sequence, for which C1 equals 1, C2 equals 2, C3 equals 4. And then from here, Cn plus 3 equals Cn plus 2 plus Cn plus 1 plus Cn. And that'll be easier for me to remember than the names of some famous mathematicians. Any questions about this one? So, like I said, I wasn't sure where to go from here. There are a number of problems, and I've listed a number of solutions, and I think that it's probably worth moving forward to a different topic. And so I'm going to do something that Fibonacci is an interesting animal. And most of what I've learned about it, I've played around and discovered. Very often, though, things were told to me about Fibonacci, and I didn't know why it was true. And very often, I didn't know why for years it was true until later I came across something, and it was almost always just playing around. And how is it that we play around with something like the Fibonacci sequence? And so let's just discuss some different ways that we can play with some numbers on paper. So, what's one possibility? One possibility is that we draw pictures. And here is an interesting picture we can draw. It's a square of length 1, let's say. We'll call this a unit square. And I'm going to draw another unit square right here. And then I'm going to keep drawing unit squares where each larger unit square shares a side formed by the previous 2 squares that I drew. So this one right here is of side length, 1 plus 1, 2. And then I'll draw another one here with side length 1 plus 2, 3. And then I'll draw another one up here with side length 3 plus 2, 5. And then 8. And then 13. And I remember the first time I saw this, I vaguely remember the first time I saw this. I know that I saw this picture several times before I was ever given, before it was ever clear to me what this picture really represented. And you can be told that it represents a whole lot of things. There are a lot of cool things. Drawing a spiral through the centers. I remember being told this was the spiral of Archimedes. And I'm sure there are things about that I still don't know. But later on I saw an interesting problem. It may have even been a problem at MOP for the early students, the level of group I was in at first. Let's see. 1 squared. That's the area of this one right here. And then the area of the next one that I drew is also 1 squared, and then 2 squared, 3 squared, 5 squared, 8 squared, 13 squared. Is that as big as we got here? Let's see. 5 plus 13, and then we got to 21. So our biggest square here was side length 21. Whole structure here, 21 plus 13 is 34. And one of my favorite principles in mathematics is one that I never heard a name for, and there may be a name for it. Maybe I just didn't have a teacher that ever gave me a name for this. I've gotten to the point where I'm just calling it the equivalent principle. And the reason I call it this is because I've seen it in different areas of mathematics get called different things. Sometimes I hear it called count it twice, or sometimes I've heard it called just find two ways to express the same thing and set them equal. But anytime you have two ways to think about the same object or the same expression, you have something interesting in mathematics. What we have here is a rectangle, and we have two different ways to compute its area. And so we write them both out, and we equate them. One of them is just to add up all the smaller components. Another is to multiply the width and length of this rectangle. And we end up with a very interesting expression because it's all Fibonacci numbers. And the left-hand side is the sum of the squares of the Fibonacci number starting at the very beginning all the way up to some Fibonacci number. And it ends up being the product of that last Fibonacci number and the next one. And that's phenomenal. And there are a lot of ways that we could prove this or demonstrate that this is true, but this picture suffices. We know that every time we add a new Fibonacci length square on, that we're just going to continue to make this a little bit bigger. So we can play with pictures. We can play with drawing things out and saying, how is it that we can see this physically, see what we can discover. We can also just play with the numbers themselves. What's a way that we can play with the numbers? What's a very natural exploration with Fibonacci numbers? Say again? Anything that we might do with a list of numbers, just to see. Very often in mathematics, it's actually the simplest things that turn out to be the most interesting. Very often when we do discover more complex things, we discover them because we started with simple things. Take the difference of successive terms. I like this answer a lot, and I like it for this reason. Earlier I said my favorite way to explore a sequence is to take a look at the evolution from one term to another. And I use the word evolution because it's different in different ways. Sometimes it's the difference, sometimes it's the way that it's growing, or constructive, like with the Fibonacci sequence. I'm going to write a simpler sequence here. If we take a look at the differences, we see that they are the same. And by definition, we have an arithmetic sequence. We take a look at the differences. And the differences are the same as the terms. Well, this is geometric. Is that always going to happen with a geometric sequence? Well, let's take a look at a different one. If we multiply each term instead of by 2 to get the next term, if we multiply it by 3 to get the next term, what's going to happen to the differences? They aren't the same as the terms here, but the same thing that's going on is we're multiplying each term by 3. So we take a look at the differences of terms in a Fibonacci sequence. And we begin to understand the sequence a little bit better, perhaps. And yet at first, I remember doing this exact exploration sometime when I was young. And looking back, at first, for a moment, it surprised me. And it seemed really, really neat. And then there was a moment at which it fit in. It made complete sense. Why does it make sense? Why is that what we just found?
Well, because if you think about it in recursion, you would have F1 and F2, or F1, F2, and F1 plus 2, and
Yeah, we could write the Fibonacci sequence from term to term. We could write it this way. We could always see that each term is a sum. That's what each term is. It's a sum. Well, we could also write it like this. We could subtract f2 from both sides. And now we see each term as a difference. In fact, the difference of two consecutive terms. And that's true for each pair of consecutive terms. f7 minus f6 is f5. So what's another exploration? What's something else we might try to do with a bunch of interesting numbers?
You could divide one by the other in a very interesting number.
So division, we saw the geometric sequences, the differences grow. We saw that they grow the same as the sequence. What are we going to find here with ratios of terms? So I'm going to write these downward. One thing I've discovered about myself is that I see data more easily when written in certain ways. And well, let's see. This divided by this is going to be 1. This divided by this is going to be 2. 3 divided by 2. 5 divided by 3. I'm going to kind of just write out decimal points and estimate instead of writing the line over them, because I feel like we're going to get to a point where maybe it's just better to be looking at the decimal form going out to some point. I'm trying. There's one more digit, but I'm going to stop there. 4. There we go. And then 34 over 21. And you know what? I'm going to quit. So somebody have a calculator? 34 over 21? Okay, so we'll go there. And this is a good start. We could keep doing this for a long time. I've done this in a spreadsheet before. Those of you who played around with Excel spreadsheets, you can very often just play with sequences like this and then produce a nice graph. And what I'm going to do is I'm going to graph these. And along this axis, I'm going to have the number of the Fibonacci term. Maybe that's the denominator. And along this axis, well, you know what? Looks like we don't have a very large range, 1 to 2. So I'll just do it like that. And let's see what happens. Well, we start at 1, and we jump up to 2, and we go down to 1.5, and we go up to 1.667, down to 1.6, 1.625, 1.615, 1.619. It's going up and down, but there's something else happening. It's not going up and it's going up and down by numbers that are smaller and smaller and smaller and smaller each time. Do we know that's going to continue? Is it always going to get smaller and smaller?
Yeah, soon it will eventually basically equal a single number, and it will change very insubstantially, leaving you with.
Yeah, it is. And how do we know that it's going to do that? It seems kind of difficult at first. How can we explore this? Well, maybe if I take, I'm going to go down here. This is F6, 7, 8, 9. Our last one is F9 over F8. And I like to look for different ways to write things. Just like I was talking about earlier, we found 2 different ways to write the sum of the squares of the Fibonacci numbers. I like to find 2 different ways to look at something. What's another way we could write this, given what Fibonacci is? Yeah.
1 plus F7 over F8.
So F9 is F8 plus F7. Now we've got F8 down here. We can split this into 2 fractions. One of those fractions is equal to 1. So, okay, that's interesting. I'm not sure it tells us why it is they're going up and down, or why it is that they seem to be approaching one number. Yeah.
Well, I think if we could see how f7, we've gone from f9 over f8 to f7 over f8, if we repeat the same thing, then the fraction will keep on flipping with the larger term on the top and on the bottom than on the top.
Okay. Yeah. So what we can say is that 1.61904 is about equal to 1 plus 1 over 1.615384. And so what does this explain why it goes up and down?
Because the fraction goes from large to small, from large to small.
So it goes up and down because it previously went up and down. And you know what? This is pretty fair, actually. What we're adding to 1 each time is changing. Well, maybe we'll write each of these this way. Maybe I'm going to write down what he said, but I'm going to do it term by term. And let's take a look. 2 is equal to 1 plus 1 over 1. 1.5 is 1 plus 1 over 2. 1.667. 1 plus 1 over 1.5. 1 plus 1 over 1.667. So let's discuss fractions real quickly. For anybody who didn't hear or wasn't quite sure what was said or what it means over here, when we have fractions, if we increase the denominator of a positive fraction, we make it smaller, so long as we hold the numerator the same thing. 1 over 2 is greater than 1 over 3, which is greater than 1 over 4, and so on. And we look right here, and each and every one of these terms after the first one can be expressed as 1 plus 1 over something. And if, for 2 terms, we see that something goes down, then over the course of those next 2 fractions, the value of those fractions goes up. We can see that for certain. This fraction is bigger than this one because this number was smaller than this one. And what that means is that this number right here will be larger than the previous term. And we end up with an alternating sequences of larger, smaller, larger, smaller, larger, smaller, larger. Let's look at the denominators, or let's look at the fractions. This fraction right here is the larger fraction. Smaller, larger, smaller, based on 1 over the previous smaller term. So yeah, it's going to go up and down, bigger, smaller, bigger, smaller, bigger, smaller. Now, does it actually get closer and closer to one single number? And this is a question, we might call this a calculus question, or maybe a pre-calculus question, depending on what your definition of calculus is. This is approaching what we call a limit, but how do we know? Is there some way that we can figure that out? Now, some of this, there's certain things that may go beyond an elementary level of mathematics that we could completely discuss here, but let's say that we can assume that we are approaching one number. It certainly looks like that. If we were to start with that assumption, could we figure out what that one number is? We've done all this exploration, and we can see a whole lot of interesting stuff in the picture, but how do we know for sure? What can we do? It's my favorite problem-solving principle. It's everywhere. Every time I look down to take out the trash, somewhere buried in there is the equivalent principle. Find 2 ways to express the same thing. Well, it's a little bit tougher here. These ratios, none of them are the same. And if we try to be too exact, maybe we're not helping ourselves as much as we could. Maybe we've got to go a little bit outside of exact. Use our imaginations. And instead of stopping at some point, we think about what things are getting more and more like as these ratios evolve. Give us a thought here.
I have an idea. You sort of have 1 plus, or I think that you use 1 plus 1, 1 plus 1 divided by 1 plus 1 divided by 1 plus 1 and so on. And that seems to, and I'm pretty sure that that should be very close to.
Yeah, this wasn't even the way that I was going to go, but it's certainly a way that we can go. If we take a look down here, here's the 9th Fibonacci number. And, oh, I'm sorry, it's the 9th Fibonacci number divided by the 8th Fibonacci number. Is 1.61904, it's approximately that. And that's equal to 1 over 1 plus 1 over 1.615384. And then we can replace this one right here, this denominator. We can replace it with 1 plus 1 over 1.625. Because this right here was equal to that. And then we can replace this, 1 over 1.625. What can we replace that with? You know what? Am I saying that quite right? Okay, yeah. This is 1 before the decimal point, and then plus 1 over 1.6. 1.625 is 1 plus 1 over 1.6. And we can keep this replacement and keep this replacement going, and eventually we get to the point where we just have ones, and that's it. And we started with F9 over F8, but eventually this is going to end. There's going to be some last one, which is actually F1, somewhere down there. This is just for F9 over F8. If we continue, if we make bigger and bigger subscripts, go out to bigger and bigger Fibonacci numbers, then we're just going to get ones all the way down, infinitely, into the abyss. So how do we evaluate that? If we look at that and we just say, this goes on and never ends, ... What can we do?
Let x equal that quantity.
Okay.
Notice that if you cut off one iteration, then you still have x. So if you substitute x into the definition of x, you have 1, or x equals 1 plus 1 over x.
So we start by giving it a name. This is a very, very old and ancient problem-solving method that probably started with babies. Be glad that your parents gave you a name so they didn't hand you back and forth saying, this thing, feed this thing, clothe this thing. We give it a name so that we can talk about it, so that we can talk about this infinite fraction right here, continued fraction is what we call it. And you know what, there's something interesting about it. When I'm looking at problems, very often I ask myself 3 questions. What's interesting about this thing? What's ugly about this thing? And what can we do about this thing? And what can we do is we can give it a name. What's interesting about it is that it looks the same within itself. It's the strange monster that looks in its belly and sees its own reflection. And we've given this monster a name. We've called it x. And now we can just say x is equal to 1 plus 1 over x. And now we have a much easier looking equation than we started with. This is, well, it's not the easiest looking equation. What can we do to make this look nicer? There's still a little ugliness here. What can we do?
I'm not sure if this will work, but x squared x squared minus x is equal to 1.
Well, and in order to see that, just a very simple, straightforward thing that we can do with this, the ugliest part of this appears to be that fraction. And a first step for reorganizing this thing is we just multiply out the fraction. Now we have an equation you can take home to meet the parents. So, well, we have a quadratic equation now, and I don't know how many of you are complete with your Algebra 1, but I'm going to rewrite it like this. X squared minus x minus 1 equals 0. And we can complete the square or apply the quadratic formula. I'll do the simple, easy quadratic formula. Did I get that right?
Yes.
We think?
Wait, yeah, that's right. Isn't there a minus?
There are a lot of different ways to write these things. I think this one is one correct form. And you know, there are two possible values of x here. And we look over here and we go, well, I just see one thing. Does it equal two things at once? Is mathematics that weird? Sometimes. It gets pretty weird. So I'm not going to answer no. I'm not going to answer no. But you know what? We weren't getting two numbers as this got closer and closer. If we estimate what these are, it doesn't take long to figure out why one of these isn't the right number. Why isn't it the right number?
Because it's negative.
It's negative, yeah. That's the simplest way to tell. Square root of 5 is bigger than 1, so when we say 1 minus the square root of 5, we have a negative number divided by 2, still a negative number. So the number we're interested in, this number right here, is 1 plus the square root of 5 over 2. And this is a very popular, friendly number. It's called the golden ratio. And it's pretty spectacular that ratio of Fibonacci numbers approaches something like this. And the golden ratio, well, turns up all over the place. It was actually, if we looked at those squares, those rectangles that we were building earlier from squares, the ratio of the lengths of the sides is one Fibonacci number to the previous Fibonacci number. And as we get bigger, the ratio of the lengths of the sides continues to approach closer and closer to the golden ratio. So we see it in shapes, and there are times when we've seen it in architecture. People have noticed it and repeated it. Though I know there's a little bit of controversy over whether or not it's really there in some old structures, but it doesn't matter to me. It's cool the fact that some people saw it and thought it was nice and interesting and used it. And in fact, the golden ratio would be the answer to the following problem. If we have a rectangle and we cut a square out of it, and the new smaller rectangle was proportional, similar to the old bigger rectangle, we can find the ratio of the lengths of these rectangles, and it turns out to be the golden ratio. And it's almost the same problem. Well, sort of. This right here actually looks more like this problem. This problem is a little bit different, but it's another way we could have viewed this problem from the beginning. So let's take a look. I'm going to get rid of this graph right here. You guys know this graph by now. So let's take a look. Width, length minus width. Well, let's see. We turn this sideways to get the smaller one up here. So we have length minus width. Let's do bigger to smaller. See the length of the bigger one over, well, that's going to be W. And we want that to be the same as the proportion of the small side of the big one to the small side of the small one. And we can cross multiply, get rid of the ugly fractions. And we're looking at this, and it's kind of like a quadratic equation, but we've got two variables. Let's ask what's interesting, what's ugly. The fact that we're dealing with more than one variable. The more variables we have, the more intimidating something seems. What can we do here? What's a thought?
Well, since we're looking for L over W, we can divide both sides of this equation by L squared, and we can substitute X for L over W, and then we get a quadratic of only one variable.
Fantastic. Focus on the goal. Our goal is this thing right here. Our goal is not to find either one of the variables. And you know what?
Or just assume W equals 1.
Or we could pick a special case. Yeah, special casing is always, well, or very often a good problem-solving principle. So yeah, we could let W equal 1, and then our ratio just becomes L. I'm going to go a slightly different route here just because a lot of you probably have enough experience with algebra that you're just getting to the point where you recognize this method several times before. Very often, the expression that I'm interested in finding, I like to give that another name. And there's a name that we very often give to the golden ratio, which is phi. I'm just going to write it like this. And I look down here, and this right here, this doesn't have phi in it. You know, maybe I prematurely cross-multiplied. Maybe I didn't want to get rid of those fractions. And you know, I could go back and not get rid of the fractions, though this denominator right here, this isn't the prettiest thing in the world. I'm just going to try to re-find what we want right here. I'm going to take everything and jam it on one side, which is what we do with most equations for a very, very long time, and perhaps even most equations after that. And then I want to get L over W. I'm going to divide by W squared. And now we've named this guy right here phi. And we can rewrite this as phi squared minus phi minus 1. And this is the same thing as our equation before, x squared minus x minus 1 equals 0. And we have the exact same roots as before. We have the exact same solution. And this right here, I said that this was also another way to approach this problem. Looking at these two ratios is the same. This is actually the one that I had in mind before somebody else said, you know what, we have a continued fraction here. And we did. And so we went that direction. But the very first time I saw phi pop out, it was by taking a look at this right here. I'm going to say some ratio of two consecutive Fibonacci numbers, big to small, is equal to the previous ratio. After all, what we were talking about in that graph was the idea that those ratios were getting closer and closer to one point. And if we just think out to infinity and say, well, that just means they're all there at that point. They are all in Fibonacci heaven. In terms of the ratios, they're all the same thing. If we start here, well, you know, we've got a lot of different variables. And, well, that's the ugly part of this. What can we do? How can we get rid of a variable? Send it out of the room. Make it 1. Unfortunately, we can't just make it 1 because we are talking about Fibonacci numbers this time. Substitute. Well, what do any one of these equal? Yeah.
Well, in Fibonacci recursion, fn plus fn plus 1 is equal to fn plus 2. So we can replace fn by fn plus 2 minus fn plus 1, and we get almost the exact same equation as the other method.
So we replace this guy up here.
Replace fn is what I meant.
Oh, I'm sorry. Yeah, we could.
We get the same equation.
I'm gonna go ahead and replace this one right here simply because I've already got this equation on the board. And we'll get the same thing. We have the same idea here. It can be done in a number of different ways that are essentially the same. And we've got fn plus 1 plus fn over fn. And that's equal to fn plus 1 over fn.
So for fn plus 1 is the first fraction here.
So this plus 1 equals this. And this is the thing that we're calling phi.
For the first fraction, isn't it over fn plus 1?
Excuse me, thank you. And we've got 1 plus fn over fn plus 1 on this side. And on the other side, we've got fn plus 1 over fn. And we can call this right here phi. And so this right here, well, these are reciprocals. So we've got 1 plus 1 over phi equals phi. And after we multiply it through by phi, we end up with a very familiar equation. Rearrange it, and we've got the exact same quadratic that we had before. Same solution. This right here, this is such a neat equation. It involves something that's hard to see without doing significant exploration. But it's still pretty simple. In fact, it kind of reminds us of the Fibonacci sequence. If we think of the Fibonacci sequence as a simplest two-variable recursion, then perhaps this is the simplest quadratic equation. And we're kind of injecting a value of simple at this point, but we do that in mathematics sometimes. We say this is special. And very often special just means it's so simple, and yet it led to something interesting. Well,
this is a good moment to take a break.
Thank you.
Take a break, and then we'll resume with the second part of the talk.
So we ended the first half of this talk with this equation right here, and it seems like a good place to start a new exploration. So I'm looking at this, and quadratic stuff is kind of the first step beyond very simple one-variable equations. Well, it's one of the first steps. We could add more variables, or we could add higher degrees of variables. When we add higher degrees of variables, we get into polynomials. And an interesting thing about this equation right here is it allows us to write any kind of a polynomial involving phi in a simpler way. And if we take a look at this, if we multiply both sides of this equation by phi, we end up with this. And looking at this, we can rewrite one of the characters on the right-hand side, this guy right here, just to get another look, just to write something in two different ways, see what we've got, and we've got 2 phi plus 1. And you know what? I don't know how significant this is, but if I were interested in cubing the golden ratio, to me it seems a whole lot easier to just multiply by 2 and add 1 than to cube it. So that's one possible point of interest, is just making things easier. Well, how far can we go with this? Well, I'm going to try to do this again. I'm going to take phi cubed equals 2 phi plus 1, and I'm going to multiply it by phi again to get phi to the 4th to see what we get. And again, I can replace phi squared. We end up with 3 phi plus 2. So I'm going to keep track of this. Let's see. Phi to the 0 is 1. I'm going to go backward, and I'm going to replace the ones that I don't have equations for yet. Phi to the 1st is phi. Phi squared is phi plus 1. Phi cubed is 2 phi plus 1. And we just found that phi to the 4th is 3 phi plus 2. Phi to the 5th. I don't know how many of you are already moving ahead and trying to compute this, but I'm going to leave this next one to you guys. I'll let you compute phi to the 5th and phi to the 6th. Maybe you guys can do different duties. Somebody can compute phi to the 7th. All in terms of phi and an integer. Yeah?
Should I do all three? Or?
Give me the first one. What's phi to the 5th? It's true. We multiply this by phi. Yeah, we have a suggestion that we've got another Fibonacci sequence. Or we could even say another one and another one. It certainly appears that way. We just do the same thing each time, multiply each equation by phi. And it is true, right here, when we replace phi squared by phi plus 1, what we have are the two previous Fibonacci numbers, 3 and 2. And then we turn 3 into, well, 3 phis and 3 ones. And we add in 2 phis. What we have is 3 plus 2 phi. So we are adding 2 consecutive Fibonacci numbers to make the next one. And then we're taking whatever the previous Fibonacci number was in this position right here, and that's our new constant. 3 times 1 equals 3. And so yeah, each time we have 2 Fibonacci numbers right here. Well, this is kind of neat on its own. And what it means is that any kind of expression, polynomial expression, 5 phi to the 7th power plus minus 3 phi to the 4th plus 5 phi plus 7, any kind of expression that involves powers of phi, we can write in terms of just 1 power of phi and a constant. We can just replace them all. What else can we do? Any other explorations that we might do beginning with this? Or, yeah? Square root this equation right here. So, you know what? I'm going to tell you right now, I haven't done that before. I have not square rooted that equation to see what I would get. Actually, I take it back. The moment I start writing it, I recognize it is something that I've done before. I just never started from that point of view. You know what I'm going to do? I'm going to leave this up here. Any of you who want to play with that right now, that's what this is about, is taking these things and just playing with them, see what you get. In the meantime, I kind of want to point this out. If I write the equation, x squared equals x plus 1, it is true that we have 2 different roots. And we've focused on one of them for now. But all of this stuff is actually true for both roots. It doesn't matter that we were talking about the golden ratio in particular. We were talking about a root of this equation. And so there's this other root of this equation, and I could write out what it is, 1 minus the square root of 5 over 2, but looking at this right here, do you guys know relationships of roots within quadratic equations? Like if I write ax squared plus bx plus c equals 0, and I have roots r1 and r2, what are some relationships with the roots that relate to the quadratic? Yeah.
R1 plus R2 is minus b over a. And R1, R2 is c over a.
Yeah, we can look at the coefficients and come up with these two relationships, the sum and the product of the roots. And I'm not going to go through the derivation of this right now. There are a lot of places you can find this online. And if you're not familiar with it, you can search Vieta. And these are called Vieta's relations or Vieta's formulas at different times. But I'm going to use this right here. I'm going to look up here, and I'm going to say there are different ways to relate the roots of this quadratic. I could say that their sum is equal to 1. The sum of the two roots of this are equal to 1. I could also say their product is equal to negative 1. C over A, negative 1 over 1. The product of the roots of this are equal to negative 1. Which of those equations sounds easier to use? What do you think?
X squared equals x plus 1. Giving the other one, you can't really find those 15. You can't find the thing with the 5.
You know, I'm not sure what you just told me, but it's probably because I may not have phrased my question correctly, and you were telling me something and I was trying to fit it into a different mental space. So start from the beginning and tell me that again.
So, given the other one, like the second version, x squared minus x times 0,
Uh-huh.
you can't really find, it's a little more difficult to find some, it's a little difficult, more difficult to do.
So you're saying that this equation is easier for exploration. Okay, you're answering a good question and not the one that I asked, so I'm gonna write this up here. That's okay. I'm gonna write this up here, and I agree that this is very interesting for exploration. We took it right here, and it very easily allowed us to take polynomials of higher degree and turn them into much simpler, or at least simpler to compute, simpler in some ways, expressions. I don't know, maybe you think x to the 7th is simpler. Sometimes it is. Sometimes 13 phi plus 8 is simpler. But in some ways, it was easier for exploration. This one right here, probably easier for computing roots. Because either we complete the square or we apply the quadratic formula. So different ways to write things, yeah, very often lead us toward different things. So it's one of the reasons I try to write things in different ways over and over and over again. And a lot of the explorations that we're going through relate to writing things in different ways. So looking up here, these two relations right here, one of them says that the sum of the roots of this equation right here, negative b over a, is 1. And then the product of the roots is negative 1. And you know, both of these are relatively simple relationships. The sum is 1, the product is negative 1. What this means is that the other root that we didn't talk about, the one that's not the golden ratio, we could write that as 1 minus the golden ratio. I'll call it R2. The second root is 1 minus the first root. Or, on the other hand, I could say R1 times R2, which is phi times R2, equals negative 1. And then if I want to take a look at that second root, I can say R2 equals negative 1 over phi. I like this second one right here for a number of reasons. I like the number 1 a lot. And really, I like both of these. There's a lot that we can do with them. But I'm looking at this right here. And when I see these expressions, I'm less interested in replacing phi with 1 minus phi. I'm less interested in that. Well, actually, I'm going to back up and I'm going to write out what I mean in terms of R. We just wrote all these relationships out. And this is true not because phi is the golden ratio, but because phi satisfied this equation right here. We kept multiplying by a root and then simplifying to lower powers of phi. But this doesn't just work for R1, the first root, which we called phi. It's also true for R2. For instance, R2 to the 0 equals 1. R2 to the first is R2. R2 squared is R2 plus 1. It's just the equation itself. R2 cubed is 2R2 plus 1. R2 to the fourth equals 3. R2 plus 2. R2 to the fifth is 5. R2 plus 3. Did I get all this right? Good. I'm going to take all these R2s. I mean, this kind of looks ugly. This is a little bit prettier right here. I'm going to replace everything with phi. Like I said, I usually think things are simpler when we just think in terms of one variable. At the very least, can help us find a lot of interesting relationships. So I'm going to replace all those R2s with negative 1 over phi, just to see what we get. Now, at first, this doesn't look all that nice. But at the very least, I have an equation that's more like this equation, more like these. Now, as we mentioned before, all these coefficients, 8, 5, 13, 8, these are all Fibonacci numbers. And I'm going to write these in a way that highlights the fact that these are Fibonacci numbers. Write things in a different way, see what you get. So phi to the 7th equals, that's the 7th Fibonacci number, times phi plus the 6th Fibonacci number. Well, I can also write another similar equation over here. If we go up to r2 to the 7th power, then what I've got is negative 1 over phi raised to the 7th power equals, what it's going to equal, it's going to be two more equations down. It's going to be the same Fibonacci number times negative 1 over phi plus f6. And of course, R2 is negative 1 over phi. So I'm looking at these two equations, and just got, well, kind of say I've got one variable, right? Well, we should be able to solve for that variable, but I don't know. What can we do with this? What's something interesting we can do with this? What if I, well, see a system of equations, and there are a number of things to do, possibly solve for a variable. We could call one of these a variable if we wanted. What's one thought you've got?
If we multiply them, we get anything interesting?
If we multiply them together, do we get anything interesting? Let's give it a try. We multiply the left-hand side, and we end up with negative 1. We multiply the right-hand side, and we're going to get, well, this times this equals negative 1. So we've got negative f7 squared. We multiply these two right here, and we get f6 times f7 phi. We multiply these two, we get minus f6 f7 1 over phi. And we multiply these two, and we get f6 squared. And you know what? We're about to discover something that I've seen before and I've proved in other ways, but never in this way. So this is neat for me. So let's see. Negative 1 equals this part right here. Now, these two both have x6 and f7. So it seems reasonable to factor those out. But, I'm going to bring this guy over right here first. And then I'll factor out these right here. I'll factor out f6 times f7. And then we've got phi minus 1 over phi. What is phi minus 1 over phi? The sum of the roots. Yeah, that's r1 plus r2 was phi plus negative 1 over phi. And what did we say that the sum of the roots was? 1. So negative 1 equals negative f7 squared plus f6 squared plus f6 times f7. Not only that, but we could do this for any Fibonacci number. It doesn't really matter that we had f7 and f6 up here, right? We could have gone up to any Fibonacci number in our equations right here. So let's take a quick look at what this actually means without getting into too rigorous a proof over this. We've got negative f n plus 1 squared plus fn plus 1 plus fn squared equals negative 1. Or I'm going to multiply the whole thing by negative 1 because I like it when the term that has the biggest bigness to it is the one that's positive. And that 1 kind of looks a little bit nicer than negative 1. Yeah?
Well, this is only true for even n, right?
I don't know. Does it matter that, and thank you, because I said something a little bit too quickly. Why do you say that?
Because we If it was 8 instead, we would have positive values rather than negative values, and we would have a different equation.
That's absolutely right. Yeah, we're going to have some sign alternation depending on what power, whether we take this to an even or an odd power, this will flip-flop in sign. And that will cause some things to be different. So this is not exactly true the way that I wrote it. Bad me.
You could just replace n by 2 in the middle word.
There we go. So we could probably even continue to write this in different ways. After all, we could write F7 in terms of F6 and F5, and we could go right from one of these to another one, which would be that F2n squared minus F2n times F2n minus 1 minus F2n minus 1 squared equals negative 1. If you replace F7 with F6 plus F5, do you like that? Is this right? It's a good thing about taking time to play around. We can always check our theories at least a little bit by computation. And that's where we get the alternation in the sign. So one good way of playing around. I love the fact that nearly everything that's been said so far has taken me in a different direction than was what was on the top of my head.
Could you return those two equations that were on top?
I was planning on that just now.
Way back to be subtracted.
Wanted to just clean things up a little bit and write them a little bit bigger. And now we can ask, what are other explorations? Now, there was a suggestion that we might subtract. Why would we do that? Why is that a very natural thing to do with these two equations? What happens when we subtract? You know, maybe do it, and then maybe it'll be easier to answer the question. Yeah. Yeah, we get rid of some of the stuff up here. And the less stuff, usually the easier to deal with or the simpler. So let's see. These guys cancel out. Well, I'm going to go ahead and factor the F7, and then we've got phi minus negative 1 over phi plus 1 over phi. Interesting. We've only got one Fibonacci number left in this equation. And we can divide both sides. We can isolate it, kind of like solving for a variable. We can take a look at what it looks like alone. Well, I mean, this is interesting, but can we make it look nicer? I mean, there's some ugliness to it. Can we clean it up?
We can use our formulas that we have in the columns with the powers of phi in terms of linear value of phi.
We could. That's where these equations came from. And if you go plugging in for these, I think what you're going to find is that the left-hand side just turns into F7. It's just going to collapse into that.
Well, we can factor, or we could write e to the 7 plus 1 over p to the 7 in terms of phi plus 1 over phi.
We could, and that is a possibility. And I'm not going to deter that exploration, but I'm going to leave a moment for something else here because there's someplace great that this is about to lead. There's so many possible explorations. I hope you guys go home and follow some of these that have popped into your head, and we won't have time to explore all of them. What is something up here that we could, yeah?
I think this is true, but We have, in general, x to the some power minus y to some power over x plus y. It's really written nicely in terms of x and y.
Yeah, I was thinking that's where you were going before. We could look at this as x to the 7th minus y to the 7th over x minus y. And the top, whenever we have a difference between two powers, it factors nicely with this in the bottom. One way to see that is any polynomial that looks like x to the n minus y to the n. If we plug in x equals y, it turns into 0. So x equals y is a root. And when you factor something into its factors, and you say, well, when is this thing equal to 0? For instance, x squared minus 13x plus 42. When is this thing equal to 0? Whenever it is we factor, what we're really asking is, when is the product of these things equal 0? I've got the product of two numbers in my hand here. When is one of them equal to 0? Sorry, when is their product equal to 0? And I gave the answer when one of them is equal to 0. Let me shout out the answer to the question. And so, yeah, when this one right here is equal to 0, well, x equals y makes that equal to 0. And so we know we've got x minus y as a factor. So we'll be able to factor that numerator and cancel out the factor, just have a polynomial. So, and that itself is interesting. We'll be able to, actually, let's do that. It wasn't where I was going. No reason it's not worth seeing. If we factor x to the 7th minus y to the 7th, we get x minus y times x to the 6th plus x to the 5th y plus x to the 4th y squared plus x cubed y cubed. If you haven't seen enough algebra to know why this is true, I think it would take too much away from the class to go through it right now. But this is what we get. And so if we divide x to the 7th minus y to the 7th by x minus y, what we're going to get is just this part. And if I plug in phis and negative 1 over phis, I'll get phi to the 6th. Phi to the 5th times negative 1 over phi minus phi to the 4th. Phi to the 4th minus 1 over phi squared, phi squared. The next one's negative 1. The next one's 1 over phi squared. The next one's minus 1 over phi to the 4th plus 1 over phi to the 6th. Oh, that's F7. It's a pretty interesting way to write F7, the 7th Fibonacci number.
It's amazing how that turns out to be an integer.
It is amazing how it turns out to be an integer. It's amazing enough that phi squared minus phi is an integer. But then again, that's kind of where it comes from in some sense. We're kind of circling back on ourselves, starting with integers. So, well, what's another thing that we can do with this right here? It's kind of amazing that it's integers. Well, let me write on the board real quickly again what phi is. I won't estimate it this time. That's exactly what it is. What's the other root? If you're not sure what to do, write something in a new way. Write it in some other way. What can we do with this over here?
Well, we can use our formula we just derived from factorization. Yes, F6, because we can write F7 as F6 plus F5, and we can use the same formula to get F5.
I'm sorry, are you calling this a formula right here? Is this what you're referring to? We could rewrite the right-hand side like this.
No, what I'm saying is we can plug in F7 equals F6 plus F5, and we can use the same formula in F5 to evaluate the matter formula for F6.
Oh, that's true. That's true. We could write all the Fibonacci numbers like this and just look at all the relationships that we already know. This one or sum of squares. lots of other ones that we could come up with. Yeah?
The denominator is just root 5, right?
Well, let's see. Phi plus 1 over phi.
Come up with a general formula for Fn.
It's not so bad. That denominator now looks a lot less scary than phi itself, I think. Well, let's just, you know what? Write things a second way. Let's just rewrite all of this stuff in terms of ordinary radical expressions. Phi is going to be 1 plus the square root of 5 over 2 to the 7th. And then minus and then phi plus 1 over phi, which is this minus this, just turns out to be root 5. Help me keep track. Do I have anything wrong yet? I will eventually, so keep watching. So f of 7 is just the difference between the 7th powers of these two things divided by the square root of 5. Well, that's kind of nice. It does give us a formula for Fibonacci. Well, let's make sure that we have this right. Am I going to have sign problems like I did before? Can't forget about those. Can I just do this? Can I replace 7 with n, replace it here and here? Are we going to get what we want?
Yes, because we didn't take the minus out.
Yeah, we didn't take the minus out this time. We were a little bit more careful than I was last time. So yeah, right now we have a formula for the nth Fibonacci number, which once again, it is phenomenal that this turns out to be an integer. If we plug in 100 and we take this weird radical to the 100th power and subtract this other weird radical to the 100th power and divide by some other radical, and we wind up with an integer, and that's pretty cool. It is. This is known as Benet's formula. And I saw this formula for years before I ever knew why it was true. And then even when I was taught one way to figure out why it was true, that just sort of started off with, if we assume that recursive series can be written in this form, and some other garbage like that. But this is really nice because it came from a very ordinary way to play with math. This was an ordinary exploration, is the type of thing that you can do on paper at home, and depending on how much experience you have with your algebra, depending on how much experience you have handling different equations, and how often it is you put together the principles that have helped you along the way, and what are some of the principles we use. Let's take a step back. Let's look at that, because that's way more important than this one result, is what is it that we did to get here? Well, we were playing around with this equation. We were also playing around with this equation, different ways to write things, and we found a way to write larger and larger powers of x, or of phi, in terms of just the first power of phi. And we did that not only with phi, but with the other root of this equation, and we looked at these side by side. And we did something that we very often do with a pair of equations or with several equations. We said, well, can we get rid of something? Make this look a little bit easier to deal with. And we subtracted off and kicked this guy out of the party. And then we were left with just one Fibonacci number in phi. And a number of things we could have done with this, but one of them is we just isolated one of the characters. We isolated F7, and we figured it out like this. And then we realized it didn't matter that we were talking about F7. We might as well have been talking about any Fibonacci number, and we could replace everything that we'd done with 7. We could have replaced with n. And it was absolutely no different. And that generalization gave us a formula. Any questions about this one? And do we have all the math right? Actually, I hardly ever remember formulas anymore. I don't remember this formula. Whenever it is I think of this formula, I actually have to do this and get these. And I'm getting to the point where I've derived it 3 or 4 times now, and so maybe I'll remember it at some point, hopefully. But when you remember how things work, and all it takes is is the same amount of work that it takes to solve a two-variable equation. You can come up with it pretty quickly, so it doesn't matter what you remember. So this is a whole lot of exploration. How much time do we have? So one thing I'm going to say about the packet I gave out today was I didn't know exactly how much this packet would cover this talk. I figured that there would be parts of it in here that would relate to the talk. I figured we'd go in a lot of different directions. One thing that you'll notice about the packets that you've got is that I've got several problem sets, and I want to tell you about those right now so that you can make the best use of them. Right after the very first problem that we did in class with the stars and the squares, I've got several straightforward, as in classical, Fibonacci exercises. After that, a page or two later, I've got a number of exercises that are at a middle school math competition, maybe Math Counts or AMC 8 level. Good way to play around and get more and more used to recursion. And if you only understood a quarter of today's talk, then most of those problems are going to be perfect for you. And for those of you who understood half or more of today's talk, there's a problem set at the end that gets pretty advanced. It begins with maybe problems that you might call very hard math counts problems or medium to difficult AMC problems, a few AME problems, and even a few problems that are more difficult than that. And for a lot of you, it's a packet that you might find value from 3 or 4 years down the road even, but there may be some of those problems you can try today. And the best thing to do with a lot of those problems is just play and explore and see what it is you find, and you may find something interesting the first time around, and it may take several explorations. But I wanted to put out that many problems and a lot with solutions that try as much as possible to highlight the principles, kind of like we've been doing as much as possible, going back and saying, what is it that we did? And usually what we did was relatively simple. So I think we've got time for 1 or 2 more explorations, and I'm going to go back to one that is a little bit easier than what we've been doing here. And earlier we took a look at what happened if we took the differences between 2 terms. We also took a look at what happened if we summed terms, squares of terms, in the Fibonacci sequence. But what we didn't do is we didn't take a look at just sums of terms. So let's say we take 1 plus 1 plus 2 plus 3 plus 5 plus 8. I'll stop there. I wanted to write long enough that it felt a little bit irritating to write. Because that's exactly the point where it's going to be a little bit irritating for you to compute, and you might actually start thinking about doing more than just the computation. And what's something we can do just to play with this? Say again? Factor in vain? Well, we don't know what will be in vain until we try it. What is it that we'd factor here? Yeah, factoring with Fibonacci numbers often does seem scary. You know, I may come back to something about that in just a minute.
Take sums of the first 10 Fibonacci numbers.
Sums of the first 10?
N.
Oh, of the first n. I'm going to come back to factoring. This right here is the first 11, and if we stopped at, oh, I'm sorry, you said n and not 10, and I'm writing factoring on the board and going back to 10. So we could generalize this and solve it more generally. So solving more generally, there are times when solving a problem more generally is actually the easier way to go than solving the problem specifically. There are times when that's true. I don't know if that's true with this in the first time around. I'm trying to imagine different approaches. If I were to write this out generally, there are approaches that I think a few people in this room would probably know and understand, but it may even depend on knowing what the sum is going to be before we start. And so I want to approach this from the position that we don't know what's going to happen here, at least at first.
We can plug in Benet's formula and notice some nice algebraic things.
Possibly. Wow. It does look like it's going to take a lot of work. There's going to be something really, really interesting that happens with that. And I'm actually going to write this up here, but I'm going to write it in terms of phi, let's see, phi to the first. Wait, did I write this first term correctly? Okay. So should it be a minus here or a plus? And it factored as x to the 7th minus y to the 7th before. Like I said, I don't even remember it until I write it down. And we'll stop at phi to the 11th. Interesting. What would be an easier way to view this, a nicer way to view this?
We'll understand denominator, and then we can put everything in our same denominator. Keep all the powers or the positive powers of phi on one side. We can move all the negative 1 over phi terms to another part of the fraction. So, and then we can have some of these eventually.
We'll group them by kind. We will separate the apples from the oranges. Minus what is this right here? This numerator, what do we call that?
Geometric sequence.
Geometric series. When they're summed, we call it a series. When they're listed, we call it a sequence. And this is a geometric series right here, and this is a geometric series. And do you guys know a formula for summing geometric series?
It's just a specific case of the factorization we talked about earlier.
You know, I'm going to do a specific example of it, a much easier geometric series than this. There is a formula for finding it. More importantly, there's a method. If we take a look at a geometric series like 2 plus 6 plus 18 plus 54 plus 162, and I'm going to take this high enough that it might seem a little bit irritating, to do the actual arithmetic. And here's what I'm going to do, something that we've done today. I'm going to give this thing a name. I'm going to call it S. And then this alone doesn't seem to do much for me. I'd like another equation to play with. And the way that I'm going to form a new equation is that I'm going to make use of what's interesting about this series. And what's interesting about this series, being a geometric series, is that it has a common ratio. And if I multiply every term in this series by that common ratio, it gives me a second equation that looks a whole lot like the first one. Oh, you look familiar. You look familiar. You look familiar. And are all these right? I hope so. If they're not, don't say anything. So now I'm going to take this first equation and subtract it from the second, and we get 3 minus 1, the common ratio minus 1, 2s. And then almost all this stuff just disappears. And we are so happy that we don't have to do all that work. Yeah, the key to motivating yourself to do a little bit tougher mathematics sometimes is recognizing that 30 minutes of work may make life so much easier later on, and that you like being lazy. And that's a good motivation for doing a little bit more hard work, right? We can be lazy later. So now we divide out the 2, and we get 4372 over 2, 2186. And for those of you who know your powers really well, that's 3 to the 7th minus 1, which is itself kind of interesting. But you know what? More generally, what we did right here, what we wound up with is the common ratio Well, if we have a plus ar squared all the way up to ar to the nth power, if we set this equal to s, multiply both sides by r, and then we subtract the second equation minus the first, we end up with SR minus S equals AR to the n plus 1 minus A. All of the other terms, A times R to all the powers before R to the n plus 1, all those terms cancel. And well, we're interested in S. We're interested in S, and we look at the left-hand side and we say, how can we get S alone? How is it that we can just look at what S would be? We factor out the S times R minus 1. And on the right-hand side, we can factor out the A, just because we can. And we divide both sides by R minus 1, and we get S equals A times R to the n plus 1 minus 1 over R minus 1. And now we see we can take a geometric series and repackage it rather nicely. And you know what? I'm going to end this one right here, because what I'd like is for some of you to go home and see how it is, what this thing turns into. And I think when you finish this exploration, you won't be particularly surprised, but it'll be kind of nice to see it all wrap up. Now, I'm going to go ahead and wrap this up here. There's a whole lot more we can talk about. I'll stick around for a little bit. Any of you who have questions about any of this, or if you have any explorations that we haven't seen, I had a whole bunch in my mind that I was just thinking, oh, these were the things that I did when I was your age. And you guys took it in completely different directions, which is awesome. But I have a whole bunch more that we could talk about. Thank you.